Hello, welcome back. Today we're going to have a topic on sampling. Okay, sampling. I'm Professor Wu, so let's get started. Now, we've seen this slide before. The US population is roughly 350 million as of 2013. That was a while ago. And if we're trying to find the average height, the point of these slides was that instead of using 315 million, very often what we could do is that we can simply use a subset of the population. So instead of entire population, we can use a smaller portion. Instead of 315 million, maybe we'll do 10,000. And the idea is that even though you only use 10,000, which is significantly smaller than 315 million, the average height should approximately equal to the actual height. And this approximation is actually turns out to be really magical. And the reason why this works, as I mentioned, is due to this rule called the law of large numbers. And the law of large number basically says that if we have an average, this is a random variable from averaging all the samples together. And that mu is the truth. So this is our average prediction, and this is the truth. Therefore, the difference between them is the error. And what the law of large numbers says is that the error, the probability that the error is greater than some tiny value. So the probability that the error is too large, right, is zero as we add more and more samples. So when you add more and more samples, the probability that you're going to have a large error approaches zero. Essentially, you can think of it that way. And because this was mathematically proven, we know that we can use a subset of population, average them together, and the difference between them is going to get smaller and smaller and smaller. Okay, so basically that's the idea from the law of large number. Now, the large number leads us to a very special conclusion. Now, remember what we talked about, that if we know the data, right, we can find the probability. We've done that in the previous couple lectures. So from the data, we can get the probability density function. So when we have the probability density function, we can calculate integrals such as the mean, right, as well as the variance. So the mean equation is xpx. We've done this many, many times at this point. So if you solve this integral, this gives you the mean. Now, if you were to solve the average distance from the center, so x minus the average, so the distance from the center square, and that will give us the variance. So we did the mean, we did the variance. Okay, so our data allows us to calculate mean variance using these two integrals. However, the law of large number, which is what we just looked at, tells us that the mean is approximately equal to just averaging all the number together. So if we just take all the numbers, average them together, right, then we approximate the mean. And if we just average the distance from the center square, if we do that, if we average them, that gives us the variance. So this leads us to realize there are two ways to calculate the mean and the variance. One is through this integral. Other is through the basically finding the mean, actually averaging them together, or averaging the average distance, finding the average distance square from the center. So this means that we have two ways, and they calculate the same thing, implying that the mean, must approximate each other, right? So this came from here, right? This came from here, and this came from here. So this is a mean, and they both calculate the same thing, and therefore, since this is approximation, this must be an approximation of this. What is interesting is let's not look at this as the mean. Let's look at this as an integral. What we're saying is that by averaging a bunch of numbers together, we solve an integral. Okay? Again, this is with mean, but here is standard deviation. If we average average the value distance from the center square, this solves an integral. Right? So what we're saying here is you can solve the integral by integration, or you can solve the integral by getting all the value from the p of x and just average them together, and you'll get the same thing. Right? So this idea, you can see that if we have expectation of x will equal to this, right? Then what we have is expectation of x minus mu square then equals to this, right? This right here is the expectation of x minus mu square, okay? And this pattern follows for any function. Expectation of any function of x is then the averaging of that value plugged into the function, averaged together. So the point takeaway here is we can approximate functions that has a probability distribution with averaging. Okay? This is like you can solve integrals the hard way, or you can just average a bunch of numbers together and you'll get the same thing. Or, sorry, approximately the same thing. Okay? So this leads what we have observed here basically leads us to a conclusion that any integral containing some p of x, if we have the data from this p of x, we average them together, it achieves the same thing as integration, right? And all you have to do is, if you have some kind of integral and a p of x, let's assume you have data from p of x, okay? You simply average that data from p of x. If you have a function and then p of x, you simply average the function. So you basically get rid of the p of x, convert this into a summation, and then you average them together. So that right there is the recipe on how you can approximate integration results that are very complicated. All right, let's use this idea a little bit. Let's pretend that I have a supplement that speeds up the brain processing power, and it has a side effect of changing the perception of time. So your brain is going faster. So the function of change is 2x plus 1, implying that if an average person perceives 1 second, that's what they experience. Your brain is going faster, and therefore the person will experience 3 seconds because it's 2x plus 1 is 3. Okay? So the first thing I want you to do is load the weight lunch data. We've done this. And at this point, you should be able to get P of X very easily. Okay. Now, if you have P of X, find the expected value using Python. So I want you to solve this integral, basically. Use Python to solve this integral. All right? And then simply average them together. So you solve them two different ways. One is through the integral, and the other way is through the averaging. And what you should get is that the integral and the averaging should approximately be equal to each other. Right? This is basically confirmation that you can solve an integral. You can solve an integral using averaging. Okay. So confirm what I just taught you yourself. Okay. So that's part one. Part two, instead of x, right? Let's see if we can do f of x, right? So this right here is the integral f of x, p of x dx. So if we're trying to solve this integral, it means that this is approximately the averaging of the function value itself. So if you just average this together, you should solve the same thing, right? And our f of x was right here, f of x. Okay, so your second goal is to show that this one is e of x, show that you can solve it two ways, and now it's e of f of x. You want to solve it this way. Okay, so you want to pause the video and see if you can really prove this yourself. I did write the code for you, but ideally you get the point. The point is that you can approximate integral with a summation, and you see it firsthand. that this did happen. Okay, that this does happen. Okay, pause the video, do this. We're going to continue with the lecture. All right, the power of using averaging for integrals. So here, in order for you to perform this approximation of integral, which is approximately equal to this, the key is you have to have samples from p of x. All right, so if you don't have samples from p of x, then you can't plug those samples in here, plug into f, and average them together. So having samples with this probability distribution is the key. And the question is, okay, what if you only have this equation and you don't have samples from p of x? What happens then? Can you still solve it this way if you have no samples? And the answer is yes. Yes. What you can do is you can take p of x, this is just an equation, and generate your own samples. Okay? So up till this point, what we've done so far is that we have data and we can use maximum likelihood, KDE, and get p of x. But what we're doing now is, let's say we have p of x. Can we get samples? Can we get data that has the same probability distribution as p of x? Okay, so you see this. Previously, we go from data to p of x. Now we're saying from p of x, we can generate our own data. And once we generate our own data, right, we can plug our data into this averaging, and we can solve the integral as well. So this is the mental picture. This is the mental picture I want you to remember. Okay, you can go from data to equation, equation back to data. Okay, so the answer is yes, you can generate own samples, and this is called sampling. Sampling is going from probability to data. Okay, sampling. Now there are many ways to generate samples. The simpler method are the ones we're going to learn, and the blue ones are more advanced. So we'll learn these ones. Okay. All right, so generating sample from distributions we've worked with previously is really easy. Go from data to generating samples. Super easy for simple distributions, like the 6 that we learned in the previous lecture. If you know the distribution, you can generate them really easily nowadays using NumPy. So for example, if we want to generate data with this Gaussian distribution, the one we will use is random. So you're going to randomly generate them, and we use normal. And if you plug in the mean and the standard deviation, let's say 0 and 1, right? And then n is the number of samples you want to generate. So over here is this. So now this, what I generate 1,000. So this right here will return 1,000 samples. And the 1,000 sample, if we just look at the first 10 values, you don't see any pattern, right? There's no particular pattern with the data. However, if we take this entire 1,000 samples and plot out the histogram, we'll get something like this. And you can see that it is centered around 0, right? And it has a standard deviation of 1. So what this is telling you is that the data generated with this, when you plot out the histogram, has these characteristics, right? Therefore, you now have the data you can essentially use to generate own samples. Okay, so over here, let's look at the code. I basically said I want this distribution to have a mean of 0, standard deviation 1, and then I generate the samples. After I generated the samples, I take the samples, and then I calculate the mean. And the mean is pretty close to 0. It's not exactly 0 because they're random. And the standard deviation is pretty close to 1, but not exactly. Once again, it's random. So your samples are going to try to look pretty close to this, especially if you have large enough samples. Okay? And then when I draw the histogram of these samples, you'll get something that looks like this. Now, if I were to draw out the equation, notice how close the P of x is to the samples. So remember, previously, what do we do? We had data to P of x. And then what we drew the histogram from the data, and then we drew P of x. But now we're doing the opposite. We have P of x, and we're drawing the data that it generated. Okay. So for simple distributions, like I said, you can use NumPy, such as, you're welcome to use NumPy unless otherwise explicitly stated not to in your homework, to essentially like generate your own sample for the simple ones. For the more complicated ones, I want you to learn essentially how to deal with those. So for exponential, to generate them, you use this one. For categorical, you can generate this way. For normal, you can generate this one. Uniform, Poisson. So you can generate all these yourself. Okay, so this is what you generate, and then we have a more like full list here. Okay, so for simple, once again, I say simple distributions, you can simply use the library. They've already do this for you. The problem is what happens when we encounter non-regular distributions, not so simple ones. Well, when you have not so simple ones, that's when, like, because there are infinite possibilities of distributions, right? So you can have quite a few common ones, but that you're always going to run into the ones you haven't seen before and there's no library for. So generating samples, you need to get the point, what the point of generating sample is, like what are we doing? And for simple ones, I don't expect you to know how to generate those. You can just use NumPy for that. Now, for hard ones, how do we deal with them? Well, before we do that, the next exercise I want you to do is I want you to generate 50,000 samples using exponential distribution. So exponential was right here, right? Exponential with a mean of 3. Okay. Now, what is the corresponding P of x? So you should know P of x pretty easily. And then from the 50,000 samples, find the average. Your average that from the data averaging should be roughly pretty close to the theoretical. And then draw a histogram P of x over it. So you're going to have something that looks like this as the data, and your line should look like this. Do that for uniform distribution between 0 and 1 as well. So generate the sample between 0 and 1. Okay, that's your next exercise. We're going to continue after this. Okay, hopefully you did that exercise. If you're just watching this at home and you think you get the point, it's very different whether you did the exercise or not. Because if you don't do the exercise, well, then like you are not realizing what you don't know, right? So, and you're not really consolidating, and it makes moving on harder. So, make sure you do this even when you're at home. All right, so the first sampling method is called the inversion sampling. The inversion sampling works like this. Let's say we have a function, this, right? This is a function, and here we will plug in the number x, and you'll give us y. This is how functions work. You plug x, and you get some kind of y value or f of x out of it. Okay, and so the key here is the direction. The direction is plug x in, get y out, corresponding y value. Okay, now that's how a function works. A function inverse, an inverse function, which is written this way. What happened is you plug a y in and you got an x out. Okay, you plug a y value, you get some kind of x out. So that's what a function and an inverse function is. And since we're working on inversion sampling, that's the first thing you need to get straight. The direction which you're getting the value. This way, the function, versus this way, the inverse. Okay? All right, so next, CDF of a probability distribution. We previously talked about the idea of CDF. The CDF is basically all the probabilities add up to that point. So let's say we have a simple distribution, Bernoulli, 0.3 and 0.7. Okay. Therefore, the CDF will be 0 all the way up till 0, right? At 0, notice it jumps to 0.3. And then all the points in between is still 0.3 until we reach 1. And then it jumps up again. Right? So all the probability up to this point is 0.3. And once you reach 1, it's going to jump up to 1 as well. And once you reach 1, that's 100% of the probability. Okay? So once again, the idea of CDF is a function where you plug the x value and it gives you all the probabilities add up to that point. So you can see if we plug 0.5 here, right, then at that point, all the probability add up to that point is only 0.3. Notice how this is 0.3, 0.3. And then once we get to 1, then you'll have 0.3 plus 0.7. It jumps to 1. Okay, so that's how a CDF function works. Okay, so the CDF gives you the probability up to x. So on the right, we have this example, which I just showed you. Notice that CDF is always between 0 and 1. No matter what, it's always between 0 or 1. Okay? And that's for obvious reason, because when you add up all the probability, it's equal to 1. So CDF is always adds up to 1, and this is because the total probability is always equal to 1. Next, notice that giving any value between 0 and 1, look at any value here. Let's pick a value. The inverse CDF will give you the value of the event, the x event. Remember, in a Bernoulli distribution, is only 2 events, right? Therefore, it doesn't matter any number you pick between 0 and 1. The inverse CDF will give you the x value. Or you can pick here. The inverse CDF will give you 0. So 0 and 1. So assuming that we just randomly generate numbers. Between 0 and 1. Like equally likely. Any number between 0 and 1. Well, if we generate this number here and we find the inverse of the CDF, it's going to say 0. It's going to be 1. And we generate it here again, it's going to be 1. But if we generate here, it's going to give us 0. So the data is going to look like 1, 1, 0, 0, 0, 1, kind of like this. And this is interesting because, well, it is generating the data we expect. However, what's more is it's generating them in a same probability. So over here, the area here is 0.3 and the area here is 0.7. Therefore, if you're anywhere, this area is 0.3, this area is 0.7. So if you uniformly generate data between like equally likely, 30% is going to fall to 0 and 70% is going to fall to 1. So notice that's the exact same proportion. 30% is going to fall onto 0 and 70% is going to fall onto 1. So the key here is you just need to find the probability, CDF, and then use the inverse. Okay, so now you generate a sample between 0 and 1. You just generate that using a uniform distribution. Plug that in. Let's say it's 0.2. So that will generate a 0. All right, now you generate x2, which let's say is 0.6. You plug that in. 0.6 inverse is 1, right? And you just do this over and over again, and you'll just generate the samples. That is called inversion sampling. Okay. let's look at a harder inversion sampling. This one was Bernoulli, which is a very simple distribution. Let's look at it from a little harder distribution, um, exponential distribution. Exponential is an easy distribution. We're using this as an example, okay? As an example. So over here, we know P of x, and from Wikipedia, you can look up basically the CDF of the function. So you know the CDF. Once you know the CDF, all we have to do is find the inverse. So we want to solve. We want to solve for x. Okay. So let's say the CDF. We're going to call that v, just to simplify the notation, and then we solve for x. Right. So v, you move the 1 here, then you take the log, which get rid of the e, and then you divide it by theta. So the equation for v, sorry, for x, the inverse CDF is this equation. This means that if you just randomly generate a number between 0 and 1 uniformly, we can essentially plug that number that you generate into v, and that will give us the sample. Okay, and that sample will turn out to be an exponential distribution. Okay. All right, let's practice generating this. Write the code that uses inversion sampling to generate an exponential distribution with mean of 0.5. First, generate sample from a uniform distribution SV. According to inversion sampling, then you basically plug V into this equation, and the result is your sample. If you collect these sample, that would be an exponential distribution. So plot a histogram, and then what you want to do is and then histogram and calculate the equation. You should see this exponential come out. Okay. All right. So that's your next exercise. And over here is the result. Notice how I generate the sample from a uniform distribution and I plug it into that equation. Now these are the samples. If I collect enough samples, notice how it generates this exponential distribution that has the mean that we're essentially looking for. Okay, so that right there is inversion sampling. Now let's move on to the next sampling method, which is called rejection sampling. To sample a complex, the rejection sampling is for like much more complex distributions than the inversion sampling. Right. So to understand rejection sampling, we first must really understand what sampling is. All right. Given a categorical distribution, like shown here, that's a categorical, with some P of X. What does it mean when we are generating random data from P of X? Like we're generating random data. We've been talking about generating data from P of X this whole time. Think about what that means. Well, it means that we're randomly going to generate n samples such that when you draw the histogram, the result of this data will mimic the equation. Okay, that's what's happening. When we draw the histogram of the data, that result will have these distributions. Okay, and once we have these samples, maybe over here is 30%, 40, 40. Okay, wait a second. I just noticed they they add up to 110. Anyways, this is just an example. I'll fix it later. Um, the point is that the distribution should mimic P of X. Okay, so the histogram, that's the key, and this can be achieved as long as we generate these sample at the same probability. So over here, if we generate the sample at 0.3, that's fine because that's the case. That's what we want. We want it to be generated at the same probability. Okay, that's a key point you must understand. Okay, then how do we go about generating sample with the same probability? Well, if you generate 100 here, think about it. If you generate 100 samples, if you accept only 0.3, so 30%, and rejects 70%, If you were to do that, then then um 70%. Then we know the probability of accepting a sample here is exactly the same as 30%. Okay, so this basically says we can generate samples randomly any way we want. But after we generate them, as long as we accept the sample at the same probability as the rate, then this sample will be generated at the appropriate probability. Okay, this is like a difficult concept to understand for some. Right? If I want to generate sample here at a certain percentage, we simply accepts the same amount of percentage and rejects the rest. Okay, this is where the core idea of rejection sample comes in. Okay, so let's note the height of each bar with its corresponding probability. Right, this is 0.3, 0.4, 0.4. They don't add up to 100%. That's my bad. I probably should have paid more attention to that, but just pretend one of them is 0.3. Okay, just pretend that one of them is different. Okay, at this point, if we let's look at this one. If we randomly generate a number between 0 and 1, and we say that if it's less than 0.3, we're going to accept. And then if it's greater than 0.3, we're going to reject. Then you see how 70% of the time you're going to reject, 30% of the time you're going to accept. Okay, which is the same probability here. Okay, now let's say over here, now that's just with one. Let's say we randomly pick this one, or this one, equally likely. So that's 1/3, right? 1/3. So, well, let's say the first one we randomly pick, and we say that okay, we pick CC++. We pick this one. Now we're at CC++. If we were to generate a number between 0 and 1 and accepted if it's that random number is less than 0.3, then we would generate these CC plus samples at a 0.3%. Now, let's repeat this process again. We'll randomly pick one of these. Let's say this time is Python, and the Python is at 0.4. So we're going to now generate a number between 0 and 1. And when we do that, we only accept if it's less than 0.4. Right? If that random number we generate is less than 0.4. And notice how then Python will be generated at a probability of 0.4. We do this again. Maybe this time it's Java, right? So you basically pick one of these randomly. Once you pick it, you decide whether you want to accept this or reject this based on the probability. Right? So right here, the real key is we want to generate samples with the same probability by whether you accept or reject these samples. So as long as you accept or reject the samples with the same probability as the actual probability itself, then you would generate those samples with those probability. Now, looking at the plot, like the key is there are two steps to this. The first step is you need to pick which sample you're generating. So you can use any technique to generate it. The easiest one is just uniform. So you randomly pick one of them, let's say Java. Once you've picked the sample, you can either accept the sample or reject the sample. And as long as you accept the sample or reject the sample at the appropriate probability that mimics its actual probability, then you would achieve a sampling of the same probability. Okay, this rejection sampling takes a while to get, but hopefully that explanation makes sense. So, so like I said, we first decide which one of these we're going to use. Then we generate a number between 0 and 1. Let's say v is equal to 0.8, right? And since 0.8 is larger than 0.4, we reject it. And when we reject it, what I mean is we're not going to add that to the list of samples. We're just going to throw it away. Okay. However, if v was less, like 0.35, then we will accept it, implying that that sample of Python is going to be added into another sample. Okay, so what we have learned now is the underlying intuition of why rejection sampling works. So now let's go over the actual rejection sampling algorithm. Let's say we want to sample from P of X. And we don't know how to sample from P of X because it's difficult. It's not one of those standard libraries. Therefore, we propose a different distribution Q. So we can sample from this. Okay, it's easy to sample from this. We then multiply Q by K, and that creates this dashed line. And K is just some number. And the idea is you want a line that is higher than your probability so you can accept or reject. Okay. Now, we don't know P, but we know Q. So we are going to use Q. We're going to generate Q to identify which one we're going to pick. So Q in this case is just uniform, 1/3, 1/3, 1/3. So we use Q to generate it. Once we generate the sample, U, let's say U is equal to C, C++. And then what we do is once we generate U, we now generate another number. So you generate second number now between 0 and 1. Well, between 0, well, 1 for this case, but it's normally K times QX. Once you generate the second one, which we're going to call it V, if V is greater than V, if V is greater than P of U, then you reject. Now, think about this. If it's P of U is this point, P of U. We just generated U, P of U is at that point. So if the value V is larger than P of U, you reject. Else, you accept. Right? Therefore, else, you accept if it falls within that range. And that right there is rejection sampling. Now, there's quite a bit of detail involved in this, and it takes a while to understand. Let's go over the steps. First, we have a P of X. We don't know how to sample from this, so we pick what we call a proposal distribution Q of X. So over here, let's say we want to generate samples from this distribution. Oh, let's say we don't know how. What I do is I know how to generate from exponential. So I'm going to create exponential and multiply the exponential by some k value. I need this k value, k times the q of x, so that it covers this distribution. It has to be higher. And the reason why it's higher is because when it's higher, you can draw a line, and this allows you to have a margin to accept and reject. Okay? So now we multiply this q of x by k. So you can pick any k value such that this line has to be larger than the probability. Sample from q of x, and then we're going to call this u. So we sample from u. After we sample from u, then that is the sample. We generate a sample. And we need to decide whether we want to accept or reject U. So what we do is we generate another number from U to KQ of X. And if it's below P of U, then we accept. Below, if it's above, then we reject. Okay, that is the algorithm, and you will have to program this at for homework. So you want to go over this a couple of times. Over here is the math on why it actually works, but if you get the intuition, that is good enough. Okay. Now, sampling is how a lot of generative models work. You may have heard of generative models, such as generating pictures, right? These are pictures. This person does not exist. These people, they don't exist. The AI generated this person. AI generated this dog. AI generated this cat. So none of these exists, right? So how are they generated? They are generated through samples. You're generating samples, and each sample is a picture. Okay, so let's say, let me give you a general idea how this works. Let's say we have some Gaussian distribution, so normal distribution, and we know how to go from the normal distribution. We know how to generate samples from this. Okay, so let's say we can have this as the normal distribution, and we can generate samples. Now, if we pass this distribution through some function, we don't know what this function is, and we're going to call this the output of this z. So input x, output z. And from z, we can get the probability distribution, p of z, given the function f, right? Given this function. Okay, so far, I started off with some Gaussian distribution. I pass it through a function, and it give us a different distribution. Nothing special there. Next, let's say we have a data, y. What is this data? Let's say this is a data set of pictures. Pictures of cats. Every single sample, one single sample is a picture of a cat, right? So there are like millions and millions of different cats. And from this, we can get a distribution P of y. So just picture we've gone from data to distribution. Now, what happens if we form an objective that looks like this? KL divergence. KL divergence measures the distance between two distributions. So if two distributions are very, very close to each other, if their distance between each other are very, very close, that means they are very similar distributions. So imagine if we find the function f that minimizes the KL divergence between P of z, P of y. What are you doing? What kind of effect can you achieve? Okay, take a second. You can think about it. All right. Now, here's the point. The point here is that if you can find a function f such that z and y have the same distribution. Okay, what does that mean? If you sample from this distribution, what happens? It means every single sample is a picture of a cat. And if you're able to make this and this the same distribution, and now you sample from this distribution, every sample is a cat. Okay? Now, if we discover the function such that if we generate a random number from a Gaussian distribution, which we know how to do. So we generate, let's say, 8, right? We put this 8 into a function. Now it gives us a sample where inside z. This gives us a sample. And this sample came from this distribution, implying that this sample, we put past 8 in here, generate a sample. This sample is a picture of a cat. It's also a picture of a cat. This means that we can just keep randomly generating samples from a Gaussian distribution. And every single time we generate a sample from a Gaussian, we pass it through a function. The output of this function is a z, which z has the probability distribution of p of z of f, which is the same distribution as pictures of a cat, implying that z that we generated must be a picture of a cat. So every single time we randomly generate a number here, pass it through this function, we generate a sample of a cat and a different cat and a different cat and a different cat. Okay, you can imagine that this some techniques similar to this. Of course, there are more modern techniques. This is a very very general idea of maybe how you can essentially make make generate your own samples, right? The generative models. So every single time I generate a random number from a Gaussian distribution, it gives me a cat that no human has ever seen before, right? So that's the general idea, and that's why sampling is so powerful. It allows you to generate new things using some randomness. Okay. All right. So I taught you inversion sampling, rejection sampling. Now let's talk about importance sampling. The importance sampling is more for solving integrals. Remember, I told you that if you have data, you can average them together to get the solve an integral. Well, importance sampling is part of that. Let's say you're trying to solve this integral here. Normally, we generate samples on p of x, and that will allow us to average f of x, and that will approximate the integral. Well, instead of doing this, let's say we don't know how to generate sample from p. We still want to approximate this. So what can we do? What we can do is we can multiply and divide by a distribution that we know how to sample. We know how to sample. Now, notice if we know how to sample this, we can combine this whole thing into a separate function which we call g. So now that means all we have to do is sample from q. We sample from q, which we know how to sample, and we average the function g. Now we can approximate the integral again, even though we're sampling from g. Okay, so this is called importance sampling. Right? This is actually really, really cool technique. Okay, so we've gone through KDE before, so let me quickly go over how you sample from KDE. With KDE, it's actually really simple. The thing with KDE is you already have the samples. Right? With KDE, you already have to. But if you want to generate more sample out of that, all you do is you randomly pick a sample. Once you pick that sample, you use that sample's location as the mean. So of a Gaussian distribution. So let's say this sample is equal to 5. So 5 is here. Now you basically generate a sample using 5 as the mean with a Gaussian distribution. So maybe you'll get 5.3. Okay. Now 5.3 becomes your first sample. Next, you pick another sample. Maybe this time you pick 8. So you put a Gaussian here, 8, and then you sample from this Gaussian, and maybe you get 7.1, right? And once you have that, that becomes your second sample, 7.1. So to generate more samples with KDE, you can do it this way. All right, in summary, sampling allows you to generate samples from P of X, right? And P of X could be anything you want, distribution of a face, people's face, distribution of speeches and novels. So you can just generate a sample and here's a speech, right? Distribution of artwork, music. Like nowadays, when you see people generating pictures, people generating music, people generating all sorts of stuff, all of that is from generative models, which you perform via sampling. Okay? And secondly, you can use it to solve very difficult integrals. So sampling is useful in these two respects. Right. Use sampling to solve an integral. Let's say we already talked about this here. This right here is saying that you can solve an integral using average. Okay. Now you can also solve integral with respect to a function instead of x, right? Using average as well. So we talked about that. This implies that you can approximate the solution of integral using averaging. So, for example, to solve the following integral. So let's say we take away the p of x. Can we still solve this even though there is no more p of x? And the answer is yes. The answer is yes, even though there's no p of x anymore. Well, what was p of x? What is f of x? Let's say f of x is this function, x squared plus 1, and we're trying to solve this integral. Well, this right here is the same as multiplying 2 and 1/2 together, right? This right here is the same as multiplying by 1. You're allowed to multiply by 1. And guess what? 1/2 is a uniform distribution between 0 and 2, right? 1/2. This right here is a uniform distribution. So what happened now, if this is a uniform distribution, there's a p of x. So the first logic, you're allowed to multiply by a value of 1. And when you do that, this turns out to be p of x. And now we have a p of x. Therefore, this whole thing can now be solved if you with a summation, right? Notice the 2 is right here. And this will be approximately equal to this integral. So all we have to do now, once we have this, is what is p of x? It's a uniform distribution between 0 and 2. So we just randomly generate numbers between 0 and 2, plug it in here, and that will solve this integral. Okay. All right. So now let's try to solve this. You're trying to solve this integral, using sampling. So pause the video, see if you can do it. The answer is in the next page. Okay? The answer is in the next page. You will see that by sampling and by the actual result, they are very, very close to each other. Write the code. Okay, I think this is almost it, right? This is write the sampling code that solves the following integral. Okay, so here's another one. See if you can solve this. In class, okay. And the very last exercise is important sampling. Okay, so see if you can solve these exercises. Hopefully you can finish. I guess that's it for today. All right, have a good one.